SpaceX recently filed for a 1,000,000 satellite network, while Axiom Space already runs active computing hardware in low Earth orbit. Down here on Earth, the staggering power demands of artificial intelligence are exhausting our physical grids, trading acres of critical land and millions of gallons of water just to keep servers running. This animated diagram illustrates that thermal overhead. Notice how a full 40% of total data center power consumption is diverted exclusively to running industrial cooling systems. Right now, engineers are hitting a thermodynamic wall. But an alternative exists, moving the infrastructure into the near absolute zero vacuum of space, bathed in continuous, high-capacity solar energy. And we are already placing early prototype processing nodes directly onto existing orbital infrastructure today. With the thermal physics now proven, the primary challenge has moved into the engineering of mass-producible tiles and affordable launch cadences. To understand how this works, we have to look at the environment. Without air or water to carry heat away, hardware in a vacuum must reject its thermal load completely through infrared radiation. This process is governed by the Stefan-Boltzmann law. The total energy radiated outward scales to the fourth power of the object's temperature. By allowing these orbital servers to run much hotter, the required surface area for radiators drastically contracts. This specific thermal reality dictates a completely different form factor, embodied by hardware like the Sophia space modular compute tile. Instead of a traditional server rack, it is a flat, passive slab. It integrates solar power generation and radiator plates directly into the unit, operating completely fanless with zero moving parts. This bar chart compares the resulting efficiency. In space, only 8% of the hardware's power is drawn for thermal management, contrasting sharply with the massive 92% required by terrestrial cooling facilities. These slabs are designed to scale rapidly, launching as single units, grouping into clusters of 40, connecting to form massive data centers. To manage a network this large, they use a proprietary software layer known as the Orbital Operating System, or SOOS, which actively monitors and schedules tasks to evenly distribute heat loads across the connected tiles. If a node takes damage from the harsh radiation of low Earth orbit, SOOS automatically reroutes the workloads. This graceful degradation isolates the damage, preventing a catastrophic chain reaction across the system. By removing liquid cooling and physical fans and distributing the compute across thousands of isolated, self-correcting tiles, the traditional data center is replaced by a resilient gigawatt-class space fabric. Right now, spinning up a compute instance in orbit costs roughly 20 times more than renting the exact same capacity on a terrestrial AWS server. The high premium is paid by early adopters facing a severe data bottleneck. Earth observation and military satellites capture incredible high-resolution imagery, but are restricted by a 40-to-1 bandwidth differential when trying to transmit that data back to ground stations. Running AI inference directly in orbit resolves this lag, compressing petabytes of raw imagery into immediate, highly actionable insights. As commercial rocket providers rapidly decrease the price per kilogram to orbit, the massive upfront capital expenditures required to deploy these tiles will drop, pushing orbital processing costs steadily downward toward terrestrial parity. Since silicon ages quickly, Orbital networks will rely on in-space servicing, using automated robotics to physically swap out degraded compute modules and solve the 2 to 3 year hardware obsolescence cycle. High-value defense and observation contracts will absorb these early growing pains. Their initial investments will subsidize the construction of a physically isolated, tamper-resistant sovereign cloud, available to anyone. This megastructure faces steep logistical hurdles. It demands a constant, flawless cadence of robotic module replacements, and deploying thousands of massive nodes drastically increases the physical threat of Kessler syndrome in our already congested orbits. The demand for raw compute is establishing an early market that analysts project will grow into a $25 billion industry by 2035. Maintaining gigawatts of processing power hundreds of miles above the Earth forces engineers to completely master large-scale off-world power routing and automated orbital construction. Developing the power and robotic systems needed for orbital compute provides the necessary technical groundwork for larger future settlements in deep space.